Tonight, we're going to look at a direction that turns out to be almost impossible to travel. On the ground, up is easy. Gravity holds you down, and up is nothing more than the opposite direction. You've never had to question it. The moment you leave Earth, that certainty disappears with it. Up stops being about gravity and starts being about speed you already have. Every world circling the sun, and every probe we've sent past it, travels within that same flat disk. That motion has been building since long before any spacecraft existed. Turning away from that disk means cancelling it first, and only then beginning to move somewhere new. Very few missions have ever attempted it, and only one has gone far enough to matter. 4 discoveries about the price of leaving that disk, and what it actually buys you. Before tonight is over, you'll know why almost nothing points away from that plane, how one spacecraft is tilting further than anything before it, and what it has found there that nobody expected. Before we go further, if wondering about the sky is something you truly enjoy, tap the like button or subscribe to the channel. It costs you nothing, and it helps this channel find more people who wonder about the same things. Let's begin. The universe was mostly empty. Then it was not. A cloud of gas and dust drifted through that emptiness for a long time. It was cold. It was quiet. It was almost nothing at all. But inside that cloud, something small began to shift. Gravity pulled at every speck of dust. It pulled at every molecule of gas. Slowly, the cloud began to fall in on itself. This is where the story of the solar system begins. Not with a planet, not with a sun, but with a slow collapse in the dark. The cloud had a very faint rotation to begin with. It was barely a motion at all. A whisper of a spin inherited from turbulence in the galaxy around it. That whisper would decide almost everything that followed. No one designed it that way. It was simply the leftover motion of a galaxy that never sits perfectly still. As the cloud collapsed, it could not simply fall straight inward. Rotating things resist that kind of simple fall. They carry a property called angular momentum. Angular momentum is the tendency of a spinning object to keep spinning. It does not like to disappear. It has to go somewhere else instead. A skater pulling in her arms spins faster, not slower. The same law was written into this ancient cloud of gas. As it shrank, its spin had to increase. And as it spun faster, it changed shape. Gravity was pulling the cloud inward from every direction at once. But rotation only resists collapse in one direction. Along the axis of spin, material could still fall freely. Toward the poles, there was little resistance. Around the equator, the spin pushed back. So the cloud did not collapse into a sphere, it collapsed into a disk instead. This happened over tens of thousands of years. That is a slow process, even on cosmic timescales. But the outcome was almost guaranteed from the start. Any rotating cloud that collapses under gravity will flatten. It has no other option. The spin will not allow a sphere to form and hold its shape. At the center of this flattening cloud, density kept increasing. Pressure and heat built up in that core. Eventually, conditions there became extreme enough to ignite fusion. A star was born at the center of the disk. That star would become the sun. Around it, the rest of the material kept spinning in its flattened shape. This structure is called a protoplanetary disk. It looked, from a great distance, like a thin plate of light. Near the center, it was thick and bright, still warm from the collapse. Farther out, it thinned into a faint haze of dust and gas. Gas and dust circled the young sun in the same direction. All of it moving together. All of it confined to roughly the same plane. Within that disk, particles of dust began to collide. Some collisions destroyed the particles involved. Others caused them to stick together, over long stretches of time, sticking one out. Dust grains became pebbles. Pebbles became small rocky bodies. Those bodies grew larger through more collisions. Eventually, some grew large enough to pull in material with their own gravity. These growing bodies are called planetesimals. Some grew large enough to clear a path through the surrounding gas. Others stayed small, drifting quietly among the larger bodies. Most planetesimals stayed close to the plane where they formed. They had no reason to leave it. Everything around them was moving the same way, in the same flattened disk. An object drifting far above or below that disk would have been rare. It would have had little material left to collide with there. Growth happened where the material was. And the material was in the disk. So the planets that eventually formed also formed close to that plane. Each one inherited the orbit of the material it was built from. Each one kept moving in roughly the same flattened path around the Sun. This is why the solar system looks the way it does today. Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, all of them circle the Sun within a few degrees of the same plane. Most of the moons in the solar system follow that same rule. So do most of the asteroids between Mars and Jupiter. The pattern is not perfect, but it is remarkably consistent. The tilt of each orbit was set early, while the disk was still forming. Later collisions nudged some of those tilts by a small amount, but the overall shape held. Scientists needed a fixed reference to describe this shared plane. They chose the plane defined by Earth's own orbit around the Sun. That plane is called the ecliptic. The name comes from eclipses which can only happen near this plane. When the Moon crosses close to the ecliptic during its own orbit, shadows align. That is where the word originated. Today, the ecliptic means something broader. It is the working reference for the shape of the whole solar system. When astronomers describe a planet's position, they often measure it from the ecliptic. When they describe a comet's path, they compare its tilt to that same plane. It is not the only possible reference, but it is the most natural one. It reflects the physical history of how everything formed. There is no wall there, no barrier, no line drawn in the dark. It is simply where the disk once was. It is the flattened path that gravity and rotation carved out, long ago. Every planet still moves close to it. Every planet still carries the memory of that early collapse. The orbits are not identical. They are tilted by small amounts, a few degrees here, a few degrees there. But none of the planets stray far from the disk's original plane. That consistency is not a coincidence. It is a direct result of how the disk formed in the first place. A cloud does not collapse into a sphere and produce a flat solar system by chance. It collapses into a disk because of the physics of rotation. Everything that forms within that disk inherits its shape. The flatness of the solar system is not an accident of history. It is a consequence of a single, simple law. Spinning things resist collapsing evenly in every direction. That resistance shaped the outer boundary of nearly everything human eyes have tracked in the sky. The planets, the major moons, the asteroid belt. All of it traces back to a spinning cloud that had nowhere else to go, but flat. Even now, billions of years later, that early geometry still holds. The disk itself is gone. The gas has long since dispersed or been absorbed into the worlds it built. The dust that once caught starlight has settled into planets and moons. But the plane it left behind remains. It is written into the orbits themselves. It is written into the steady, repeating paths of every planet around the Sun. The ecliptic is quiet now. No storm of dust moves through it anymore. Just worlds, tracing the same flattened road their material once formed within. The Sun sits near the center of that road, holding everything to its pull. a road with no edges and no true way to leave. That idea will matter more as this story continues. For now, it is enough to picture the shape. A thin disk of light around a new star. Everything within it moving one way, together, in the dark. The gas cooled, the dust gathered, and the pattern held. Nothing since that early collapse has erased it, and from that shape, the whole quiet order of the solar system took its form. Every spacecraft carries a kind of budget. It is not measured in dollars, but in speed. Engineers call it delta V, a term that sounds technical, almost cold, though its meaning is simple. Delta V is the total change in velocity a spacecraft can produce using its own engines over the whole life of a mission. Every burn spends some of that budget, and every course correction spends a little more. Once the budget is gone, the craft can only coast. It cannot speed up. It cannot slow down. It cannot turn. This is why mission planners obsess over the number, checking and rechecking it long before a single engine ever fires. They treat it as the one figure that cannot be borrowed back later. A spacecraft with too little delta V is stranded, drifting wherever momentum carries it. A spacecraft with enough delta V has choices. It can climb. It can dive. It can bend its path around a distant world. Delta V decides what is possible and what is not. Think of it as fuel, translated into motion, not fuel by weight, but fuel by effect. A heavy tank means nothing on its own. What matters is how much speed it can buy. Some destinations are cheap in this currency, reachable with only a modest push at just the right moment. Others are extravagant. And the most extravagant of all lies straight up, not up in the sky as seen from a rooftop, but up out of the flat disk of the solar system. To understand why, consider the Earth. Right now, this moment, Earth is moving. It circles the sun at nearly 30 kilometers each second, faster than any bullet ever fired. The planet does not feel like it is racing, since gravity holds every ocean and mountain in place. But relative to the sun, the motion is immense. Every spacecraft launched from Earth inherits that speed the instant it leaves the ground, and there is no way to leave the ground without taking it along. This inherited speed is a kind of gift, pointing sideways along the plane of the planets. That sideways direction has a name: the ecliptic. Nearly everything in the solar system lies near it, the planets. Most comets on short, tame orbits, countless smaller bodies, drifting in the same general band. The ecliptic is a wide, flat racetrack, and every world runs its laps in nearly the same plane, following the same general direction around the sun. A spacecraft aimed at another planet uses this gift well, borrowing the sideways speed it already has, and adding only a modest push in the same direction. The math favors the traveler. Mars, Jupiter, even distant Neptune, all sit near this plane, and reaching them means adjusting speed within a single, shared lane. It is like changing lanes on a highway, where the car ahead and the car behind share the same road. A small nudge moves you from one lane to another, and the engine barely has to work against the flow of traffic. Now imagine a different goal. Not another lane, but leaving the highway entirely. Not sideways, but straight up, out of the plane. This is where the budget changes completely. A polar solar orbit means circling the sun from pole to pole, with the craft crossing above and below the ecliptic instead of staying within it. To do this, a spacecraft cannot simply keep its inherited speed. That 30 kilometers per second points the wrong way, along the plane, not away from it. Before the craft can climb out of the plane, it must slow that sideways motion, not by a little, but by a great deal. Only after cancelling much of that speed can new motion begin. Only then can the craft aim toward the poles of the sun. That is the real obstacle underneath all of it. The craft is not adding motion to nothing. It is fighting motion that is already there. Undoing 30 kilometers per second is not like adding a small push. It is like braking a speeding train before turning it sideways, and the braking itself devours enormous energy. That energy is spent long before the turning can even begin, and none of it goes toward the new direction yet. Compare this to a simple trip toward Mars. A spacecraft bound for Mars keeps its sideways speed and uses it as part of the journey. Nothing is wasted cancelling out what was already helpful. A spacecraft bound for the poles of the sun cannot do this. Its inherited speed becomes an obstacle rather than an aid. And the very momentum that makes planetary travel easy makes polar travel hard. This asymmetry surprises people at first. Up sounds simple. Up sounds like the easy direction, the direction of least resistance. In the solar system, up is nearly the hardest direction there is. Distance is not the difficulty, since the sun's poles are, in raw distance, closer than many outer planets. The difficulty is angle, the need to fight existing motion before making any new motion at all. Engineers describe this with a simple phrase: plane changes are expensive. Even a modest tilt in orbit costs real delta V, and a steep tilt costs far more still. Such a tilt carries a craft well out of the ecliptic and toward the poles. At high speeds, the cost multiplies, because Earth moves fast within its plane. Because of that speed, a large tilt is punishing, and the faster the sideways motion, the more it costs to redirect it. This is simple physics, but its consequences are strange. A journey outward, deeper into the solar system, can be gentler than it sounds. A journey merely upward, barely leaving the plane, can be brutal. Speed, not distance, sets the price, and direction, not depth, decides the difficulty. A spacecraft could, in principle, brute force the problem, carrying enormous amounts of propellant and cancelling that sideways speed through raw engine power alone. But propellant has mass, and mass has to be lifted from Earth in the first place. Every extra kilogram of fuel demands its own fuel to launch, and that fuel demands still more fuel. The numbers grow absurd very quickly, and the costs compound with every added kilogram. Rockets capable of hauling that much propellant grow to impractical sizes. At some point, the rocket needed no longer fits any launch pad on Earth. This is why polar solar missions are so rare, not because the destination is unreachable, but because the price, paid in velocity, is severe. Mission planners weigh this price against the value of what might be learned. The answer is not always yes. Sometimes the answer is worth it. Often the answer is not. The sun's poles remain some of the least visited neighborhoods nearby, held back not by distance but by momentum, by a debt in delta V that few missions can afford to pay. It is a strange kind of barrier, invisible, made only of motion, not matter, yet as real as any wall. No hull could ever be built strong enough to push through it directly. The solar system does not forbid travel outward from its plane. It simply prices it far beyond what most journeys require. And it does this quietly, without ever announcing the cost in advance. Every planet, every moon, every distant traveler obeys the same quiet accounting. Speed borrowed must eventually be spent. Speed spent in the wrong direction must first be undone. Only then does a new path become possible. This is the invisible cost behind a very visible idea. Going up sounds effortless. In the solar system, going up is the hardest motion of all. The gap between those two sentences is where the real cost of exploration hides. written not in metal or money, but in the quiet arithmetic of velocity. Ein/texti, Ein/invoke. There is one path through the solar system that almost nothing has ever taken. Not outward, and not inward, but up. Every planet moves in roughly the same flat plane. Earth traces its orbit there. So does Mars, and so does Jupiter. So does nearly everything else that circles the Sun. That flat plane is called the ecliptic. From far away, it looks like a thin disk of dust and rock and ice. Spacecraft are built to move within that disk. They launch along it, they coast along it, and they arrive along it. Almost every mission humanity has ever flown has stayed inside that shape. But one spacecraft did something different. Its name was Ulysses. It was built by the European Space Agency, with help from NASA. The year was 1990. Its goal was strange, almost impossible to picture at first. Leave the plane entirely and rise above it. Look down on the Sun from a place no spacecraft had reached before. The Sun has poles, just like planets do. There is a North Pole and a South Pole. From Earth, we never see them directly. We only ever see the Sun's equator, its middle band, the wide face turned toward the plane where we live. The poles stay hidden, tilted away, never quite in view. Ulysses was built to change that. It would fly up and over the Sun's North Pole. Then it would dip down and pass beneath its South Pole. No instrument had ever measured that geometry up close before. But there was a problem. Rising out of the ecliptic is not like turning a car onto a side street. It takes an enormous amount of push to bend a spacecraft's path that far. Rockets alone were not going to be enough. The mission needed something else, a shortcut written into the shape of the solar system itself. That shortcut had a name, and its name was Jupiter. Jupiter is the largest planet by far. Its gravity reaches for enormous distances, bending the paths of anything that comes near. Engineers realized they could use that. Instead of fighting Jupiter's pull, Ulysses would fly straight toward it. It would let the planet catch it, and let the planet turn it. This kind of maneuver is called a gravity assist. A spacecraft swings close to a massive body. The planet's gravity curves its path. The spacecraft leaves in a new direction, carrying momentum it did not have before. Usually, gravity assists are used to speed a spacecraft up, or to send it further out. Ulysses used one for something else entirely. It used Jupiter's gravity to twist its path sideways, out of the flat disk, up out of the ecliptic altogether. The spacecraft launched from Earth in 1990. It carried instruments built to sense particles, magnetic fields, and the invisible weather blowing outward from the Sun. For more than a year it traveled outward, away from Earth, away from the inner planets. It was heading toward Jupiter. Not to study Jupiter itself. Jupiter was only ever meant to be a turning point. Eventually, Ulysses reached the giant planet. It swept past, closer than most missions ever come. Jupiter's gravity took hold of it. The planet's mass bent the spacecraft's trajectory in a way no engine on board could have matched. There was no burn, no thrust, no engine firing to force the turn. Just the pull of a planet, and a spacecraft passing near enough to feel it. Ulysses left Jupiter moving on an entirely new path. The flat plane that every other mission respected no longer applied to it. Its course now rose at an angle nothing had flown before. It took years for that new path to unfold. In time, Ulysses reached its first great milestone. It passed high over the Sun's south pole. No spacecraft had ever been in that position before. Below it, the Sun's surface curved away in a way no observer had ever measured from that angle. The instruments recorded fields and particles that behaved differently there than anywhere else studied before. The spacecraft continued on, curving through space, carried by the momentum Jupiter had given it. Years later, it swept back around. Ulysses passed high over the sun's north pole. For the first time, a single mission had surveyed both, from directly above and from directly below. That is a vantage point the ecliptic never allows. What made this possible was not new engines, and it was not new fuel. It was one pass by one planet, at exactly the right angle, at exactly the right moment. Jupiter did the work that no rocket could. Its gravity reshaped an entire trajectory in a single encounter. Ulysses continued to orbit through this tilted path for years afterward. It circled back toward the poles again, and then once more. Each pass added more data. Each pass confirmed how different conditions above and below the sun really are. But that maneuver at the center of it all was never repeated. No other spacecraft has used Jupiter to climb out of the ecliptic since. No mission has again tilted itself so far from the plane where everything else moves. Ulysses remains, even now, the only spacecraft that has ever truly gone up in the solar system. Not up in the sense of altitude above a planet's surface, but up in the sense of leaving the shared plane entirely. It rose above the disk that holds Earth, Mars, Jupiter, and nearly everything else in place. It is a strange kind of solitude for a spacecraft to carry, alone in an orientation nothing else has chosen, tilted against the grain of the whole system, passing over regions of the sun that remain, to this day, unseen by any other instrument. The maneuver that made it possible depended on timing so precise it could not simply be repeated on a whim. Jupiter had to be in the right place. Earth had to be in the right place. The angle of approach had to be exact. All of it lined up only once for one spacecraft built for exactly that purpose. Since then, missions have returned to the familiar plane. They orbit where the planets orbit. They travel where the traffic of the solar system already flows. The open space above and below remains almost entirely unvisited. Ulysses passed through it once, briefly, and then moved on. The data it gathered still shapes how scientists think about the sun's poles today. The vantage point itself has not been revisited since. For decades now, that space above the ecliptic has stayed quiet. No new spacecraft has climbed there. No new gravity assist has bent a path skyward. Just the empty geometry Ulysses once passed through, waiting there, unclaimed. The same way it was before 1990 ever began. Somewhere in the archives, its instrument readings still sit. The only record of that angle on the sun. No telescope on Earth can recreate that view. Only a spacecraft leaving the plane can see it. And only one ever has. It launched once, from Earth, and rose where nothing else had. A single spacecraft, a single pass by Jupiter, and a view of the sun no one has seen the same way since. The plane below stayed crowded with traffic. The space above stayed empty, holding the memory of one quiet crossing. Somewhere out past the orbit of Mars, that same geometry still waits. Jupiter still turns on its axis, still bends the paths of anything that passes close enough. No mission has been built to use it that way again. The window that opened once for Ulysses has simply stayed closed. Engineers still study its numbers, still trace the shape of that single turn. The sun still spins with its poles half hidden from the crowded plane below. Nothing built since has climbed high enough to look at them directly. Nothing built since has needed to try. The one detour ever taken through the solar system remains, for now, the only one. Distance is not the same as sideways. That distinction sounds small at first, but it is not small at all once you sit with it. A spacecraft can travel for decades, crossing tens of billions of kilometers, and still remain close to the plane it started in. Far is easy. Sideways is the hard direction. 5 spacecraft have left the inner solar system behind, on their way to somewhere past the last planet. Each one has covered a staggering distance. None of them has strayed far from the flat plane it began in. Voyager 1 left Earth long ago. It flew past Jupiter, then past Saturn, then kept going, outward into the dark. Today it is farther from the Sun than any human object has ever traveled. A slight tilt above the plane came from that journey, and the tilt is real. Still, it stays modest, nowhere near a path toward the poles of the solar system. Nothing about the route was built for that kind of climb. The tilt is worth noticing precisely because it stays so minor. A whisper of sideways motion beside decades of forward travel. Saturn's gravity shaped the trajectory because engineers wanted a close look at the moon Titan. That choice bent the path upward, slightly, just enough to leave the flat disk of the planets. The mission's character never changed because of it. Voyager 1 drifts sideways to the Sun, but only by a few modest degrees. Voyager 2 tells a related story, though its shape is its own. 4 giant planets welcomed it in turn: Jupiter, Saturn, Uranus, Neptune. A full grand tour no other spacecraft has matched. Each flyby used gravity to adjust the course, nudging the angle a little further every time. By the time Neptune fell behind, a small tilt of its own had gathered. That tilt carries the spacecraft gently away from the plane. Never toward it, never across it dramatically. Call it a slow, patient drift, outward and slightly up, year after quiet year. 2 long journeys, 2 small angles, both barely registering against the vastness around them. Neither mission was ever meant to go sideways. Distance was the assignment, along with flybys, and the worlds strung out along the way. Pioneer 10 crossed the asteroid belt first, and reached Jupiter first too. After that flyby, it continued outward, into the emptiness beyond. Its signal has been quiet for many years now, faded and finally gone. The path continues anyway, carrying it onward whether anyone listens or not. Distance-wise it is immense, sideways its displacement stays small. Pioneer 11 followed a related route, visiting Jupiter and then Saturn. Saturn's gravity bent that course too, much as it later did for the Voyagers. Near the plane it remains, all the same, its small angle barely worth mentioning next to the distance it has covered. Far from the Sun, yes. Far to the side, no. A newer example comes from New Horizons, which offers the same quiet pattern in a different key. Pluto was the goal, far out at the edge of the known planets. The spacecraft reached it after a long journey, then kept going past it. A small, distant, icy world further out came next, glimpsed briefly on the way through. Both encounters held it close to the plane, because the mission needed exactly that closeness. Pluto orbits near the plane, roughly speaking, and the distant object beyond it does too. So the path stayed roughly flat the whole way out into the dark. New Horizons is now far beyond Pluto, moving fast, its distance from the Sun growing every day. Its angle above the plane has barely shifted since. A small figure that keeps refusing to grow no matter how far the craft travels. 4 different missions, 4 small tilts, 1 shared story running underneath them. Going up or down was never the point for any of the 4. None of them needed it. Their science lay outward, along the plane, past the planets and their moons. Moons waited there, quiet and numerous. Rings waited too, thin and pale. Icy, ancient bodies drifted there as well, patient in the dark, waiting to be found. So the paths went outward, mission after mission, following the disk instead of leaving it. Here is the pattern worth sitting with. Going far is the easier problem, once a spacecraft is already moving. A rocket burns once, Gravity assists add speed at each planet along the way. The spacecraft coasts for years, for decades, without needing to be told to keep going. Distance accumulates on its own, given enough time. No further effort is required. The universe does the rest, patiently, without complaint. Going sideways does not work that way. There is no coast phase for that. Every degree of tilt away from the plane has to be paid for, at the start or later. Either way, it is never free. Distance, by contrast, can be almost given away, accumulated quietly while nothing new is spent on it. There is a simple reason for that difference, older than any spacecraft. Nearly everything in the solar system orbits in roughly one plane. That plane is a leftover from how the solar system formed, long before any of this began. A spinning cloud flattened itself, long ago, into a wide, thin disk. Planets, moons, and spacecraft alike still move within what that disk left behind. A spacecraft launched from Earth begins inside that same disk, sharing Earth's own motion around the Sun. That motion is fast, and it is entirely within the plane from the very first moment. To leave the plane, a spacecraft must cancel some of that shared motion. It cannot simply slow down and speed back up. It has to turn, in effect, at something close to a right angle to where it is already going. That kind of turn costs far more than going faster ever could. Going faster keeps the direction the same. Turning changes the direction entirely. Engines are not well suited to that kind of change. Gravity assists are not naturally suited to it either. Most flybys bend a path only a little within the plane, or just slightly out of it. Bending it far out of the plane takes a very particular kind of encounter. Few of those exist along the routes spacecraft actually fly. Mission planners rarely attempt it, for exactly that reason. They design for outward motion from the very first sketch of a trajectory. Heading outward suits the tools they already have. It lets gravity assists work the way they work best, planet after planet, in sequence. A spacecraft passes new worlds this way, one after another, strung along the disk like beads on a long, dark thread. Leaving the plane would mean leaving that string of worlds behind. It would mean crossing mostly empty space, with little left nearby to study. For a mission built to see as much as possible, that trade rarely makes sense. So spacecraft go out, again and again, mission after mission, decade after decade. They do not go up or down in any serious way. Voyager 1, Voyager 2, Pioneer 10, Pioneer 11. New horizons. 5 long careers, one shared shape traced quietly against the dark. They stretch outward from the sun like spokes from a wide, slow wheel. Barely any of them lean far from that wheel, even after all this time. The spacecraft drifting outward tonight carry that same shape with them. Silent, distant, moving along the plane, always the plane. Never far from it. Even after decades of travel. Even after billions of kilometers already crossed. The angle stays small, night after night, while the distance keeps climbing on its own. Out there, past the last bright planet, the dark keeps moving too. It does not hurry, and it does not turn. It only continues, carrying its small, quiet cargo further from home, always within the same wide, flat plane. There is another way to climb. It does not rely on one great push. It relies on patience. Solar Orbiter, built by ESA and NASA together, chooses patience. It does not attempt a single steep escape. It leans on a smaller world instead. Venus becomes its quiet partner. Not once. Not twice, many times. Each time Solar Orbiter passes near Venus, something small happens. The planet's gravity gives the spacecraft a nudge. The nudge is gentle, It bends the orbit just a little. It tilts the path a few degrees higher. Then Solar Orbiter falls back toward the Sun. It swings around. It returns to Venus again. Another flyby. Another small tilt. The spacecraft repeats this pattern year after year. Where one probe once used a single giant leap through Jupiter's pull, this one climbs in small steps. Each step is modest. Together they add up. This is the slow method. It trades speed for repetition. It trades one bold move for many careful ones. Every pass near Venus costs energy and time. Mission planners accept that cost. They know the tilt will come slowly. They know it will come surely. Degree by degree, the orbit rises. There is no way to hurry a planet. Venus moves on its own schedule. Solar Orbiter simply waits for the next window. Each waiting period lasts months. Engineers use that time to check instruments. They calibrate sensors between encounters. They plan the next approach with care. Nothing is left to chance. The spacecraft's solar panels tilt to manage heat during each close pass. Its heat shield faces the Sun directly. Behind that shield, the instruments stay protected and cool. Every flyby brings its own small risks. Distances must be exact. Timing must be exact. A pass too close could pull the orbit the wrong way. A pass too far could waste the opportunity entirely. Engineers model each encounter for months before it happens. They run the numbers again and again. By the time Venus arrives in view, the plan is already set. By February 2025, the results were clear. Solar Orbiter had reached an inclination of 17 degrees above the Sun's equator. 17 degrees may sound small. In this field, it is remarkable. Most spacecraft built to study the Sun stay below 7 degrees. They orbit close to the solar equator. They see the Sun the way we usually picture it. A flat disk. A familiar face. 17 degrees changes that picture. It lifts the spacecraft's view above the usual plane. It opens an angle no other solar mission had reached. Slowly, the poles began to come into view. For centuries, the Sun's poles had stayed hidden. Every telescope on Earth looks at the Sun from nearly the same angle. Every probe before this one had orbited close to that same flat plane. The poles were always at the edge of sight, blurred and foreshortened. No one had ever looked straight down at them. Solar Orbiter's repeated Venus flybys were built to change that. Each tilt brought the spacecraft closer to a clear view. Each pass made the poles a little less hidden. By early 2025, the angle was finally steep enough. The spacecraft could look down toward the bottom of the Sun. It could see territory no instrument had captured before. On March 16 and 17, 2025, that moment arrived. Solar Orbiter turned its instruments toward the Sun's south pole. 3 instruments worked together for this task. Phi mapped the magnetic field at the surface. UE captured extreme ultraviolet light from the outer atmosphere. SPICE studied the different layers of hot gas. Together, they built the first clear images of the pole. No spacecraft had ever produced pictures like these. The view showed a churning, complicated surface. It did not look calm. It did not look uniform. Bright and dark regions mixed unevenly across the pole. Magnetic patches pointed in different directions at once. North and south polarities appeared tangled together. This was new information about a region long assumed to be simple. Older models had pictured the pole as steady and orderly. The real pole looked restless instead. Scientists had modeled the poles for decades without ever truly seeing them. Now they had a direct look. The images did not answer every question. They raised new ones. But they gave researchers something solid to study. They gave the Sun's poles a face for the first time. Capturing the images was only the beginning. The data still had to travel home. Solar Orbiter was far from Earth when it recorded these observations. Its instruments had gathered enormous amounts of information. Sending it all back takes time. The spacecraft has a limited communication window. Data trickles down in careful, scheduled bursts. Engineers prioritize what to send first. They balance urgency against bandwidth. Some files wait their turn for weeks, others move ahead in the queue. Piece by piece, the pictures and measurements made their way to Earth. A complete dataset from this first pole-to-pole pass finally arrived in October 2025. Months had passed between the observation and its full delivery. Only then could scientists study every detail at once. Only then could they compare every instrument's results side by side. They lined up the magnetic maps beside the ultraviolet images. Patterns that were invisible in one dataset showed clearly in another. Teams across different countries worked from the same files. Each group checked the data against its own models. Slowly, a shared picture of the pole began to form. The weight mirrored the mission itself. Nothing about this approach was fast. Nothing about it was sudden. It was built from small steps, repeated with discipline. Venus, again and again, gave a small assist. 17 degrees, reached slowly, opened a door. 2 days in March produced images decades in the making. Months of transmission turned raw signals into usable knowledge. Each stage required waiting. Each stage required trust in the process. There was no shortcut available. The tilt could not be rushed. The poles could not be seen without it. The data could not arrive before its time. Solar Orbiter's method shows a different kind of achievement. No sudden jump at all. A long series of quiet adjustments. Each flyby is unremarkable on its own. A pass near Venus, a small gravitational tug, a slightly steeper path. Repeated enough times, these small events change what is possible. They allow a spacecraft to see what nothing had seen before. The Sun's south pole, mapped in magnetic detail. Its shifting brightness, recorded by ultraviolet light. Its layered atmosphere, traced by spectral instruments. All of it made visible through patience. All of it made visible through repetition. Going up, in this part of the solar system, does not mean going fast. It means returning to the same gravitational partner, over and over. It means accepting a small gain each time. It means letting those small gains accumulate across years. Solar Orbiter is still climbing. Its orbit will keep tilting with future Venus flybys. Higher inclinations are still to come. Clearer views of both poles are still to come. The North Pole still waits for its turn. Future flybys will bring that view into focus too. Each new pass builds on the one before it. The mission does not restart with every flyby. It simply continues, adding one more careful step. For now, the achievement stands on its own. 17 degrees of tilt, 2 days of historic observation, months of careful data return. All made possible by a method built on patience, not force. The Sun's poles, hidden for so long, are finally being mapped, not through a single powerful push. Through Venus, again and again, through many small steps, taken slowly, taken carefully, taken again. Solar Orbiter is not finished. Its path was set years in advance. Long before any single flyby became news, engineers had already mapped what would happen next, and when. Every turn in that path was planned before the spacecraft ever needed to make it. The next major step waits on the calendar, December 24th, 2026. On that day, the spacecraft returns to Venus. It will not land. It will not even come especially close. Distance is not the point of this encounter. Angle is. Solar orbiter sweeps past the planet, and Venus pulls at it with gravity alone. That pull bends the flight path slightly upward, not in altitude, but relative to the flat plane where the planets orbit. Before this flyby, the spacecraft's tilt is smaller. After it, the tilt grows. The mission calls this number inclination. It measures how far a path leans away from flat. 0 degrees means a path that never rises above the plane. Most spacecraft never leave that flat plane at all. Solar Orbiter was built to leave it. After the December 2026 flyby, inclination reaches 24 degrees. 24 degrees does not sound large. In orbital terms, it is enormous. It opens views of the Sun that no flat mission could ever capture. It opens views of the poles that no telescope on that plane has ever recorded. But 24 degrees is not the end goal. It is a waypoint. The mission has already planned the next one. June 10, 2029. By that date, another shift will have occurred. Solar Orbiter will orbit at 33 degrees. 33 degrees is a steep lean, well above the plane most spacecraft never leave. From there, entire regions of the Sun become visible for the first time. Those regions stay hidden from every other angle, no matter how close a spacecraft flies. Reaching that angle costs something. The cost is paid in a specific currency. It costs another pass by Venus, timed years in advance to meet the spacecraft exactly where it needs to be. Solar Orbiter carries only so much propellant. Every kilogram of it had to be weighed against everything else the spacecraft needed to carry. Propellant alone could never lift it this far. So the mission borrows motion instead of burning it. It draws on the planet's own orbit to do work the engines were never designed to do. Each Venus flyby is really an exchange, small on the scale of a planet, decisive on the scale of a spacecraft. The people who planned this mission gave the method a name. They call it repeated gravity assist. They chose it deliberately over a single dramatic maneuver. That bolder option was considered and set aside early in the mission's design. One giant push toward a steep angle would have demanded fuel the spacecraft was never built to carry. Spreading that cost across years asked for something cheaper than fuel. One modest flyby at a time. It asked for time. The spacecraft launched with that trade already written into its trajectory. Every subsequent encounter follows logic laid down before liftoff. A long stretch of quiet travel follows each flyby. Little seems to change from one week to the next during that stretch. Still, the spacecraft keeps working through every orbit. It observes the Sun from whatever angle it currently holds. Even a modest tilt reveals something a flatter path would have missed. 24 degrees will not stand alone. It builds on encounters already completed. It will itself become the foundation for 33. Nothing in this mission happens suddenly. Everything accumulates across years of careful timing. Venus does not know it is being used this way. It simply continues its own orbit. It stays indifferent to the spacecraft crossing its path again and again, on a schedule fixed long before either date arrived. Mission planners chart these encounters years ahead of time, long before the public hears about any single flyby. December 2026 was calculated years earlier, alongside every other encounter in the sequence that leads toward it. June 2029 was calculated at the same time. It is part of the same long chain of dates, fixed well before the spacecraft nears either one. Both sit on a chain that began soon after launch, a chain with no shortcuts and no leaps. A vantage point far above the plane, where the planet's orbit waits at the far end of that chain. No direct route can reach it. From up there, the Sun looks different than it does from anywhere else. Structures that blur together on the flat plane begin to separate cleanly at height. Motions that seem chaotic from below start to show their pattern once the spacecraft climbs above them. That view was not possible without the climb that came before it. And the climb itself was not possible without Venus. The planet returns again and again on its own schedule, unaware of the role it plays. The spacecraft gives up nothing of its own to gain that view. It only waits. It arrives on time. It lets the planet's motion do the rest. More encounters remain on the schedule after 33 degrees. They stretch years beyond June 2029. Each one follows the same quiet arithmetic that has carried the mission this far. A pass by Venus. A small bend upward, a longer look at the sun from a slightly higher place. The roadmap extends further than any single flyby could show on its own. It is built one careful pass at a time. There is no shortcut anywhere along the way, and there was never meant to be one. Somewhere in Mission Control, a folder holds the dates of encounters that have not happened yet. Those encounters will not make headlines for years. Each one already has a number attached to it, an inclination it will help the spacecraft reach. Each one already has a place in the sequence, waiting for its turn. The spacecraft does not know these numbers. It only follows the trajectory it was given. It adjusts slightly with every pass, correcting drift that accumulates between encounters. Ground teams track that drift constantly. They compare the real path against the planned one, degree by degree, orbit by orbit. Radio signals carry the data across millions of kilometers, arriving minutes after they left the spacecraft. Small corrections keep the two aligned. Larger corrections are rare because the plan itself was built to need few of them. Engineers on the ground rarely need to intervene beyond those small nudges. A rushed trajectory would need constant fixing. A patient one, laid out years ahead, mostly holds its shape on its own. Solar orbiter's climb toward the poles is not a straight line. It is a slow spiral, widening by fixed amounts at fixed moments. Each widening ties to a specific date and a specific pass by Venus. 24 degrees in December 2026. 33 degrees in June 2029. Numbers further out exist too. They belong to years still distant enough that little has been written about them publicly. Some of those later dates sit almost a decade past the one on the calendar now. The spacecraft will reach them the same way it reached everything before. For now, the next milestone is close enough to matter. December 24th, 2026 sits on the calendar like any other date until the spacecraft reaches it. Then a small bend in a distant orbit becomes a wider view of a star that never stops burning. The spacecraft will not celebrate the moment. It has no way to. It will simply hold its new angle and keep watching. It will watch the way it has watched from every angle before this one. It will watch the way it plans to keep watching from every angle still to come. A spacecraft turns its gaze toward the sun. It tilts its orbit away from the flat plane where the planets travel. This lets it look down on a place rarely seen. The south pole of the sun comes into view. Scientists have waited decades for this angle. Earlier missions passed near the poles but could not see them clearly. They caught only glancing views from the side. This one carries instruments built for the task. It measures magnetic fields directly, from close range. The readings begin to arrive. Researchers expect a clean pattern. A single dominant polarity, north or south, gathered at the pole. That is what a simple magnet would show. That is what models of the sun have long assumed. The data tells a different story. The pole is not clean. It is not orderly. It is a tangle. Patches of one polarity sit beside patches of the other. North and south lie mixed together, side by side. There is no single direction to point to. There is no neat boundary. Instead, there is a kind of magnetic weather, small regions shifting in orientation across the same stretch of surface. The scientists studying the images call it disordered. It is a strange word for a place expected to be simple. But the sun rarely stays simple for long. This messiness is not a flaw in the instrument. It is a real feature of the star. To understand why, it helps to think about how the sun's magnetism behaves. The sun is not solid. It has no fixed crust to anchor its magnetic field in place. It is a churning ball of plasma, charged gas in constant motion. That motion generates electric currents. Those currents generate magnetic fields. The whole system is fluid, shifting, alive. Because of this, the sun's magnetism is never still. It builds, twists, and eventually releases. Then it builds again. This process follows a rhythm. Roughly every 11 years, the pattern repeats. Scientists call this the solar cycle. At one end of the cycle, the sun is calm. Its magnetic field is more organized. The poles hold something closer to a single polarity each, north at one pole, south at the other, like a bar magnet. This calm phase is called solar minimum. Sunspots are rare during this time. The surface looks quieter, more settled. But the calm does not last. Inside the sun, motion never stops. Layers of plasma rotate at different speeds. The equator spins faster than the regions near the poles. This uneven rotation drags magnetic field lines with it. Over time, the field lines stretch. They wind around the sun like thread pulled tight. The once simple field becomes twisted and complex. Sunspots begin to appear. They mark places where twisted field lines break through the surface. Their number grows as the cycle progresses. Eventually, the sun reaches its most active phase. This is called solar maximum. Sunspots are numerous. Flares and eruptions become more common. The magnetic field is stressed, tangled, full of competing directions. At the peak of this activity, something remarkable happens. The magnetic poles of the sun flip. North becomes south. South becomes north. This reversal happens roughly every 11 years, in step with the cycle. It is one of the most striking features of our star. No planet in the solar system does this so often or so completely. The sun turns itself inside out again and again on a human timescale. Each reversal is not sudden. It unfolds slowly, in stages, over months. The old field weakens before the new one takes hold. For a while, neither polarity is fully in charge. The pole seen by the spacecraft was caught mid-transition, not at the calm of solar minimum, not at the settled aftermath of a completed flip. It was caught somewhere in between. This explains the tangle of polarities. The old magnetic order was breaking down. A new order had not yet formed. For a period, the pole holds both signatures at once. Fragments of the outgoing field. Fragments of the field taking its place. This is not chaos without meaning. It is a snapshot of transformation. A magnetic field pictured mid-collapse, still tangled from the reversal. Understanding this messy phase matters for a larger reason. The solar cycle affects more than the sun itself. It shapes the flow of charged particles streaming outward. It shapes the strength and shape of the solar wind. These effects reach every planet, including Earth. They influence satellite operations. They influence power grids. They influence the auroras that shimmer near the poles at night. Predicting solar activity depends on understanding how the cycle unfolds. Forecasters watch the poles the way sailors once watched the sky. Small changes there can hint at what is coming months later. And that means understanding the poles. The poles are where the old field lines gather and cancel. They are where the new field lines take root. If the poles are hard to observe, the whole cycle is harder to predict. For a long time, they were nearly invisible. Spacecraft mostly traveled in the same flat plane as the planets. From that vantage point, the poles are always seen edge-on. Their details blur into the limb of the sun. Small patches of polarity simply could not be resolved. Tilting an orbit out of that plane changes everything. It offers a view straight down onto the pole. It lets instruments map the scattered patches of polarity directly. It turns a blurred edge into a resolved surface. Each pass adds more detail to the picture. Engineers plan the trajectory over years before the spacecraft ever leaves Earth. Gravity from Venus is used to bend the path upward. Each flyby lifts the orbit a little further from the plane of the planets. It is a patient way to reach a steep angle. There is no shortcut for tilting an orbit around a star. The disordered pole is, in a sense, good news for science. It confirms that the transition between cycles is gradual, not instant. It shows the process unfolding in real time. Small regions of magnetism jostling for dominance. Neither polarity fully in control. The picture will not stay this way. As the cycle advances, one polarity will slowly win out. The tangle will simplify. The mixed signals will sort themselves out, one small region at a time. A single, cleaner field will settle at the pole again. For a while, the sun will look orderly once more. Then the slow twisting will begin again. The equator will outrun the poles. The field lines will stretch and knot. Sunspots will multiply. The cycle will build toward its next reversal. And the poles will grow messy again, right on schedule. This rhythm repeats roughly every 11 years, cycle after cycle. Long before instruments existed to record it, the sun was already turning this way. Long before anyone looked up and wondered why the sun's face seemed to change. Now there is a spacecraft positioned to watch it happen. Tilted out of the plane, looking down on a place once hidden from view, recording the disorder exactly as it is, watching it shift week after week. Each new pass over the pole adds another frame to a very slow film. No single image tells the whole story. It is the sequence, gathered over months and years, that reveals the pattern. Instruments log the strength and direction of the field at thousands of points across the pole. Researchers compare each map to the ones that came before it. Slowly, a shape starts to emerge from the noise. The pole holds no single answer yet. Only a mixture, shifting slowly, on its own long clock, north folded into south. Most planets keep to one plane. They circle their star like plates spinning on a table. That habit comes from how planets are born. A young star sits inside a flat disk of gas and dust. Planets form from that disk, so they inherit its shape. The result is a system that looks almost two-dimensional from above. But that flatness is a habit, not a law. Gravity itself has no preference for flat orbits. It pulls the same in every direction. Nothing in physics forbids a planet from tilting far out of that plane. A steep, unusual path is allowed by the same rules that hold ordinary orbits together. Astronomers have found a case where that happened. The planet orbits a pair of stars. Not just one. Two suns, bound together, orbiting each other closely. Around them both, this world moves on a path unlike any nearby. Instead of circling near their shared plane, it goes over the top and under the bottom. It travels from above the stars to below them and back again. That kind of path has a name. Astronomers call it a polar orbit. The name comes from the way the planet passes near the poles of the pair, rather than near their equator. Here it is not a technical curiosity. It is a real planet, moving that way right now. To understand why that matters, picture the shape it replaces. In most binary systems, a planet orbiting both stars stays close to their orbital plane. It goes around the outside, like a ring around two dancers. This planet does something else entirely. It climbs above the pair, arcs across and dives below them. Then it climbs back up on the far side. At some point in its loop, the planet crosses the plane where the two stars sit. That crossing is brief. For a short stretch, the planet passes near the line between the stars. Seen from the planet, the two suns would draw close together in the sky. Their light would blend for a while. Then the planet moves on, and the suns separate again. Most of the orbit is spent far from that crossing point. During those stretches, the two stars sit apart from each other in the sky. One might hang near one pole of the sky as seen from the surface. The other could sit far across, near the opposite side. The pattern of day and night there would not resemble Earth's. Sometimes both stars might be visible together. At other points, only one would be up at all. The rhythm of light and dark would shift as the planet moves through its tilted path. There is no simple sunrise and sunset to describe. Instead, there are two light sources, moving independently across a sky shaped by this odd geometry. A traveler standing on such a world would have no fixed reference for up or down relative to a single sun. The horizon itself would carry two different rhythms, one for each star. None of this required special conditions to occur. It required only that gravity be allowed to do what it always does. Two stars pull on a planet from different directions. If the planet's path starts tilted enough, that pull can hold it on a polar course. The stars keep it bound. They just do not force it into their own flat plane. For a long time, this kind of orbit existed mainly in calculations. Researchers had modeled polar orbits around binary stars using orbital mechanics alone. The math showed such paths were stable. A planet could hold a steeply tilted orbit for a long time without being thrown out of the system. Stability on paper is not the same as proof in the sky. Plenty of things survive in a model without ever appearing in nature. Finding a real example changes that. It shows the geometry is not just permitted. It is something that can actually happen when a planetary system forms. Confirming an orbit like this took years of patient observation. Astronomers do not simply see a planet directly in most cases. Instead, they watch the light of the stars themselves. A planet passing in front of a star dims that star's light slightly. The dip is small, often a tiny fraction of the star's total brightness. Instruments record that brightness night after night. Over months and years, a pattern can emerge from the noise. Because two stars are involved here, the light itself is more complex. Both stars contribute brightness, and both can be blocked at different points. Researchers had to separate the light of one star from the other. They tracked how the combined brightness changed over repeated orbits. Small, regular dips pointed to something crossing in front of the pair. The timing of those dips carried information about the planet's path. Dips that lined up only with certain points in the binary's own cycle suggested a tilted orbit rather than a flat one. Modeling that timing took careful, repeated checking against years of data. Alternative explanations had to be ruled out one by one. Only after that process did the polar orbit interpretation hold up. The find did not come from a single clean image. It came from patterns pulled out of small changes in starlight over a long stretch of time. That is often how orbital shape gets confirmed at this distance. There is no probe near enough to send back a photograph. There is only light, arriving after a long journey, carrying faint signatures of motion. Reading those signatures requires attention over years, not moments. Each new season of observations either strengthened the pattern or weakened it. Slowly, the weaker explanations fell away, leaving one shape that fit the data best. Once confirmed, the planet became something more than an unusual data point. It became evidence that nature can produce what theory only allowed. Flat disks are common, and they tend to make flat systems. But disks are not perfectly uniform, and binary stars complicate their shape further. Two stars pulling on a forming disk can warp it, tilt it, or disturb it in ways a single star cannot. Under the right conditions, a planet can end up on a path far from that original flat plane. Once it settles into a stable polar orbit, gravity keeps it there. The two stars continue to hold the planet on its steep, looping course. There is no force pulling it back toward the plane over time. The orbit persists because the physics that created it also sustains it. This single confirmed case does not mean such orbits are common. Most planets found around binary stars still orbit close to the shared plane. Flat orbits remain the ordinary outcome of how these systems form. But ordinary and only possible are different things. This planet shows that the range of what can exist is wider than the average case suggests. It sits at the edge of the ordinary, proof that edges are still real places. Somewhere among all the systems yet to be studied, other planets may follow similarly steep paths. Some may be found through the same patient tracking of starlight. Others may take longer, hidden in data not yet fully examined. For now, this one confirmed world stands as a marker. It shows two suns, a tilted path, and a planet that visits both the top and the bottom of its system on every loop. It moves quietly, far from Earth, following a geometry once known only as an equation. It is a reminder that what physics allows, nature will sometimes go ahead and build. Now it is also known as a place, real and orbiting. Exactly where the calculations said it could be. Far past the planets, the sun's light grows faint. Out here, distance stops making sense. Miles no longer help. Even the scales used near the planets fall short. You are entering the Oort cloud. It is the most distant region of the solar system. It is also the least understood. Nothing has ever traveled far enough to see it directly. No probe has crossed that gap. No telescope has either. Everything known about it comes from calculation. It comes from indirect clues gathered over generations. From comets that fall inward and reveal where they came from. From orbits traced backward across centuries of observation. From models built slowly, one clue at a time. Patience is the only tool that works here. Certainty comes later, if it comes at all. The inner solar system has a simple shape. Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, all of them circle the Sun in nearly the same flat plane, like plates arranged on a table. A thin disk, spinning slowly in the dark. The planets formed from that same flattened disk of gas and dust. Rotation pulled the material into a plane early on. Everything since has followed that shape. The Oort cloud does not follow it. It breaks the pattern completely. Instead of a disk, it forms a shell. A hollow sphere wrapped around the whole solar system. Comets can enter this shell from any direction. Not only along the plane where the planets orbit. They can fall from above, from below, from every angle at once. This is one of the clearest signs of its shape. Astronomers have tracked long-period comets for years. The pattern never favors one flat band of sky. They arrive scattered across the whole sky. Their orbits are tilted every possible way. Some are steep. Some are nearly upside down compared to the planets. That randomness could not come from a disk. A disk would send comets in from certain directions. A sphere sends them in from all directions. The evidence points to a shell, not a ring. Astronomers describe two rough zones within it. An inner region, somewhat flattened, closer to the old disk shape. An outer region, fully spherical, indifferent to any plane at all. The inner zone still remembers where it came from. Its orbits lean slightly toward the plane of the planets. The outer zone has forgotten that history. Out there, no direction is favored. Up and down lose their meaning. A comet could fall from above the sun's pole, or from directly below it. Either path would be equally ordinary. The outer shell marks the true edge of the sun's pull, a region so distant it may stretch halfway to the next star. Sunlight thins to almost nothing out there. The sun looks like just another star. One point of light among countless others. Objects drift in near silence. Motion becomes slow beyond imagining. Temperatures settle near the coldest point space allows. Nothing here hurries toward anything. So how did a flat disk become a hollow sphere? The answer is not sudden. It built up slowly, over billions of years. In the solar system's early history, things sat closer together. Icy bodies formed nearer to the giant planets than they do now. Jupiter and Saturn were still settling into their orbits. Their gravity was immense. Every icy body that passed near a giant planet felt a pull. Sometimes that pull nudged an orbit outward. Sometimes it flung an object away entirely, lost for good, scattered into interstellar space. Others were pushed out just far enough to survive. Far enough that the sun's gravity still held them, though barely. They carried the memory of that scattering in their orbits. Long, looping paths stretching far beyond the planets. Each loop took them out into the cold and back again. A journey measured not in days, but in ages. At that distance, other forces began to matter. The gravity of nearby stars, passing over millions of years, the gentle pull of the galaxy itself. These forces are weak on their own. They do not need to be strong. They only need time. And this region has time in abundance. Each pass by a distant star tugged at these bodies, bending their orbits a little further from the plane. Not all at once. Not in any dramatic way. A fraction of a degree here. A fraction there. An orbit that once lay flat began to lean. Repeated across billions of years, the orbits lost their alignment. They tilted. Then, tilted further. Eventually they pointed in every direction. What began as a disk was reshaped into a shell. This kind of process never appears sudden. It only appears finished, looking back. No spacecraft could ever witness this shaping directly. The changes unfold far too slowly for any human timescale. A single orbit out here can take millions of years. A mission would need to outlast civilizations to see one loop. The forces work on the clock of stars drifting past each other, on the slow turning of the galaxy itself. This is why the Oort cloud stays theoretical. Not because scientists lack certainty about its existence. The evidence from comet orbits is strong and consistent. But observing its shape directly would take far longer than a lifetime. Longer than many lifetimes strung together. Entire generations would pass in the meantime. Whole centuries of watching would still show almost nothing moving. The reshaping never stopped. It is still happening now. Slowly, invisibly, tonight. Somewhere in that shell, an orbit is bending by some tiny fraction. Too small for any instrument to catch. Somewhere out there, an icy body drifts. It knows nothing of planets or plans or planes. It has never felt sunlight strong enough to warm it. It only answers to gravity, thin and unhurried. Around it, countless other bodies drift the same way. Each one alone. Each one held by threads of gravity too thin to notice. Yet never absent. Spread so widely that collisions almost never happen. space enough between them to swallow entire worlds. The shell holds its shape through constant, quiet redistribution. Objects settle into every possible tilt, every possible angle. A sphere made not of design, but of time. Somewhere in that vast, dark shell, the sun's pull fades. Beyond it, only starlight remains. The solar system's edge is not a wall. It is a slow fading into the space between stars, held together by gravity so thin it is almost imaginary. Every icy body out here is still part of one system, bound by threads too thin for any instrument to trace easily. Still orbiting, however slowly, however far. The shell has no edge you could point to and name. It simply thins, mile by mile, until nothing remains to hold. Beyond that, the pull of other stars finally takes over. Rest here a while longer. The shell keeps turning above you. Silent, unhurried, endless, electric propulsion works differently from a chemical rocket. There is no single burn, no sudden shove that changes everything at once. Instead, ions are ejected in a thin, quiet stream, one after another. Each ion carries away a tiny amount of momentum, and the spacecraft gains the opposite in return. It is a small nudge, barely a whisper of force. You would not feel it. Standing on the hull, a coin resting on a table would not even slide. But the engine keeps running. Hour after hour, day after day, it does not stop for sleep or pause for weather. It simply continues, steady and unremarkable, doing the same small thing again and again. Xenon gas is the usual fuel, sitting in its tank inert and calm. A small amount is fed into a chamber and given an electric charge. The charged atoms are called ions. Electric fields push them out, and they exit at extremely high speed, far faster than any chemical exhaust could manage. Speed is what makes this work. A little mass, moving very fast, still pushes back hard. The thrust itself stays tiny, barely enough force to lift a coin. That is the trade being made here. Chemical rockets choose power. Electric engines choose patience. A chemical engine burns its fuel in minutes, and the delta V arrives all at once. An electric engine spreads that same delta V out, stretching the change across months. The total push, added up over time, can rival a chemical burn. It simply arrives on a different schedule, spread thin across a much longer stretch of the mission. There is no shortcut here. No single moment of transformation. Only accumulation. Small increments layered one after another until they add up to something real. Each orbit is slightly different from the last. Each pass a little more inclined than the one before. A spacecraft on electric power spirals rather than leaping between orbits. It winds outward or upward, slowly, tracing a path that looks less like a line and more like a widening coil. From a distance, the shape is almost lazy, and nothing about it looks urgent. And yet it works. Given enough time, the inclination climbs, orbit after orbit, without any single dramatic step. Mission planners accept this trade willingly, because they are not chasing speed. They are chasing efficiency instead. An electric engine sips its propellant, so a tank that would last minutes on a chemical engine can last months here. Less mass needs to be carried, and less mass means more freedom for the rest of the spacecraft. Room opens up for instruments, for shielding, for whatever the mission did not expect to need. The result is a spacecraft built around patience, gaining a little more velocity every day and reshaping its orbit in small, steady increments. There is no drama in this, no countdown, no dramatic ignition, just a low current, flowing steadily, and ions leaving quietly, one stream at a time, for as long as the mission requires. The engineers who plan these missions watch numbers, not fireworks. The pace is slow enough that a single day tells almost nothing on its own. Only the long view shows the climb. Solar sails take a different approach entirely, carrying no propellant at all. Instead, they rely on light. Sunlight itself carries momentum, and photons striking a surface transfer a tiny push with every impact. A single photon barely matters on its own. But sunlight is constant, photon after photon, arriving without pause across the whole life of the mission. A large, thin sail can catch enough of them to matter. The sail unfurls in space, reflective, lightweight and vast in area. Every square meter gathers a small amount of force. Spread across many square meters, that force adds up. Still, it remains gentle, nowhere near the strength of an engine. But gravity itself is gentle over long distances, and this force never runs out of fuel to work with. As long as sunlight reaches the sail, the push continues. There is no tank to drain and no valve to fail. Only geometry and light doing their slow work together. The angle of the sail decides the direction of the push. Tilt the sail, and the force tilts with it. A sail angled correctly can nudge a trajectory out of its plane. Patiently, without any single decisive moment. Slowly, the orbit tips. No planet is needed for this, and no close, risky pass by a massive world. Just light and time, and a carefully held angle, held steady for as long as the maneuver takes. This appeals to mission designers for a simple reason. A slow method is often a controllable one. Every small change can be measured, and every small change can be corrected before it grows into a problem. There is no irreversible moment where everything is decided at once. There is only a long, gradual adjustment, checked and rechecked as it unfolds. Course corrections become easy this way. A slight change in the sail's tilt or in the ion engine's throttle brings only a small consequence. Almost everything stays reversible. This is very different from a single powerful burn. A burn, once fired, cannot be taken back. A slow accumulation can be watched the entire way, step by step, with room to adjust at nearly every stage. Engineers check the numbers daily, comparing the actual path to the one they planned. If something drifts, it can be nudged back gently, without urgency. If something stalls, there is time to notice and time to respond. Time itself becomes the tool here, not brute force, and not a single explosive moment. Ion engines hum faintly in the dark, invisible from any distance. Solar sails catch light that no one else even notices, tilted just slightly off the sun. Both are moving a spacecraft, fraction by fraction, away from the plane it once followed. Neither method is fast, and neither draws attention to itself, but both work, given enough months and enough patience to let a tiny push become a meaningful one. The spacecraft does not fight its orbit. It leans on it, gently, again and again, each lean small, each lean safe. This is how a small force becomes a real change over time. Not through strength, but through repetition. A whisper of thrust, repeated enough times, becomes a shift in course. A whisper of light, caught enough times, becomes a shift as well. There is no single instrument that announces the change. No alarm, no readout that spikes. Only the patient comparison of 1 week against the last, and the quiet confirmation that the orbit has moved. Nothing dramatic ever happens out here. Nothing needs to. Patience like this asks little of the spacecraft and much of the people watching it. A crew waiting for a chemical burn knows the outcome within minutes. A team watching an ion engine or a solar sail waits through weeks that look identical to each other. The numbers move by fractions, and the fractions are the whole story. Trust has to be placed in the process itself, not in any single reading. Over a full mission, that trust is repaid. The orbit that seemed unreachable at the start becomes, slowly, the orbit the spacecraft is actually in. No single week proves it. The full stretch of months does. This is the quiet logic behind choosing electric propulsion or a solar sail in the first place. Neither promises a fast answer. Both promise a steady one, provided enough time is given to let the small pushes stack. A tank of xenon that outlasts any chemical fuel supply changes what a mission can even attempt. A sail that never needs refueling changes it again, in a different way. Together, they represent the same idea approached from two directions. One through charged particles, and one through captured light. Both trade urgency for endurance. The change simply accumulates, unhurried, in the dark. One small step folded into the next. The sun keeps a rhythm that most people never notice. It beats slowly. Once every 11 years, give or take, its magnetic field flips. The North Pole becomes south. The South Pole becomes north. Nothing on the surface announces this. There is no flash, no sound, no visible seam in the light reaching Earth. The change happens deep in the structure of the star, and it happens completely. For a long time, humans could only guess at how this reversal unfolds. They watched from the plane of the planets, level with the solar equator. From there, the poles are barely visible. They sit at impossible angles, foreshortened, half hidden behind the curve of the sun. For centuries, that was the only view available. Every observation of the poles was a reconstruction, not a direct look. Scientists took readings from far away and worked backward toward what the poles might be doing. It was careful work, but it was always a step removed from the thing itself. Solar Orbiter changes this. Its path carries it above the plane where the planets travel. It tilts higher with each pass, gaining a new angle on the sun no probe has held before. From this angle, the pole comes into view. Not as a smear of light at the edge of the disk, but as a place with its own shape, its own structure, its own story unfolding in real time. For the first time, instruments are watching the polar magnetic field directly, at the source, as it prepares to turn. The old method relied on inference. The new method relies on sight. That difference changes what scientists can actually know. They can trace the old polarity as it weakens. They can trace the new polarity as it takes hold. They can follow whether the change spreads evenly across the pole or moves in patches, unevenly, over time. They can compare the two poles directly, watching to see if one turns before the other. These were questions the equatorial view could never settle with confidence. The angle was wrong for it. The data was always partial, filled in with assumption where direct sight was missing. Every prior estimate of the polar field carried a kind of asterisk. It was pieced together, not observed. Solar Orbiter removes that asterisk. It puts a set of eyes directly above the place where the turning happens, and lets the process speak for itself. Each orbit lifts the spacecraft a little higher above the equatorial plane. Each pass adds another slice of the pole to the record. Over time, those slices begin to form something closer to a full picture. Not a single snapshot, but a sequence. A pole caught mid-change, frame after frame, across months and years. This 11-year cycle is not a quiet, private matter of the sun's internal architecture. It reaches outward. It touches everything the sun touches, which is to say, it touches the whole solar system. The same magnetic cycle that governs the flip also governs how active the sun becomes. As the field builds and twists on its way toward reversal, the sun grows more active. It produces more solar flares. It produces more ejections of solar material out into space. These bursts of activity can reach Earth. When they do, they can disturb satellites in orbit and power grids on the ground. The tangled field that eventually reverses is the same field that, along the way, drives the flares and eruptions. Watching the poles closely means watching the earliest stage of that tangle. Long before a flare erupts near the equator, the shift that will eventually produce it is already forming near the poles. A clearer view of the poles offers a clearer view of what is still to come. Scientists can watch the old polarity lose its grip, region by region. They can watch new magnetic structure take hold in its place. From that, they can begin to estimate when the cycle will crest. They can begin to estimate how strong the coming peak might be. This is not simple curiosity. It is a kind of preparation, built on data that only this vantage point can gather. Before Solar Orbiter, that early signal simply did not exist in this form. Warnings came later, closer to the peak, when less could be done to prepare. A direct view of the poles pushes that warning earlier, closer to the quiet beginning of the change. There is a second layer to this work, quieter than prediction. By watching the field reverse in detail, scientists are also testing older models of how the sun works. Some of those models were built entirely on equatorial guesses. Now they can be checked against something closer to the source. Some will hold up. Others will need to be revised. Either outcome adds to what is actually known, rather than assumed. The reversal itself asks nothing of the rest of the solar system. It happens whether or not anyone is watching. It happens whether or not a spacecraft has climbed high enough to see it. The sun has flipped its poles for as long as it has had poles to flip, long before there was anyone nearby keeping count. But now, for the first time, that ancient rhythm is being watched from a vantage point built to understand it. Not glimpsed sideways, not inferred from indirect signs. Observed at the source, one slow reversal at a time. Watched not just as a single event, but as a process with a shape, a pace, and a rhythm of its own. The poles turn. The field settles into its new shape. And 11 years later, quietly, it begins turning again. You have watched the sun from the side for a long time. Every mission before this one stayed close to the ecliptic, that flat plane where the planets circle. It is the easy path. It costs less fuel. It gives clear views of the equator, but it hides the poles completely. For decades, the north and south of the sun stayed out of view, and scientists could only guess what was happening there. They built models. They ran simulations. They filled the blank spots with inference where direct sight could not reach. Inference is not the same as seeing. A guess can be close. A guess can also miss in ways nobody expects until later. Sometimes not until the storm is already on its way. The solar poles are not decoration. They are control centers. Magnetic field lines gather there and reorganize, breaking down and rebuilding over time in a slow, uneven churn. That process shapes the solar cycle. It shapes when storms grow strong and when they go quiet. Without seeing the poles, that whole process stayed half hidden, described only through what could be measured from far away. Solar Orbiter changed the angle. It climbed out of the ecliptic plane, little by little, over years of careful maneuvering. Each pass by Venus mattered. It bent the path a little higher. By the year 2025, it reached a tilt worth watching. In March, it looked down on the sun's south pole, seeing it directly for the first time from above rather than from the side. 3 instruments did the work. PHI measured the magnetic field at the surface. EUI captured the extreme ultraviolet light above it. SPICE studied the layers in between, tracing temperature and motion through the same patch of sky. Together, the 3 instruments did not just take a single picture. They built a structure out of what they saw. Magnetic strength, temperature gradient, plasma flow, all layered over the same patch of sky, each instrument adding a dimension the others could not reach on their own. The polar magnetic field turned out to be tangled and uneven, not the neat pattern anyone had drawn on paper, not the smooth single pole scientists once assumed. Patches of opposite polarity sat mixed together, overlapping in ways a distant proxy could never have shown. Timing mattered here. The sun was in the middle of shifting its field when Solar Orbiter looked. Not a flaw. That messiness is simply the sun caught mid-transition, not an error in the data. Seeing it directly means the models can finally be checked against something real. For years, forecasters built estimates of polar field strength almost entirely from indirect proxies. They watched magnetic patches drift toward the poles from lower latitudes, tracking that drift over months, sometimes years, then estimating what it meant for the pole itself. It worked, roughly. But roughly is not the same as accurately. A small error at the pole can grow into a large error in a forecast, one that shows up only after the storm has already reached Earth. The difference between observing the poles and inferring them from the ecliptic is not a small technical detail. It changes what forecasters can actually predict. A model built on direct measurement starts from what is true, while a model built on inference starts only from what is likely. Those are not the same foundation. Solar storms begin as small disturbances buried deep in the magnetic field. They travel outward as bursts of charged particles. Some head toward Earth, and when they arrive, they can disrupt satellites. They can push extra current into power grids. They can scramble radio signals used for navigation. Better warning time means fewer surprises. It means operators can prepare the grid before the current spikes. It means satellite operators can angle solar panels away from the worst of it. And airlines can reroute polar flights before a storm even hits. None of that works well without accurate models of the sun's poles, built from something firmer than a distant guess. The improvement starts with direct observation. A camera pointed straight at the pole rather than sideways at its edge. That single shift changes what the models can trust. The data from that March flyby is still being processed. A single pass does not reveal an entire pole. Solar Orbiter saw one hemisphere from one angle. The far side of that pole remained in shadow, out of view for now. As the spacecraft continues its orbit, the angle will shift again. Each pass adds another strip of coverage. Layer by layer, pass by pass, the picture slowly builds. Scientists compare each new image against the last. They track how magnetic patches move. They watch how brightness in the ultraviolet band changes over weeks. Small changes matter. A patch that brightens may signal rising magnetic tension underneath, while a patch that fades may simply mean the field there is settling. None of this shows up cleanly in a single snapshot. It shows up over a sequence, one image compared patiently against the next. That is why mapping the full pole will take years, not months. The team expects the analysis of the March data alone to continue for several years. Every new pass will need to be checked against what came before. Slowly, the tilt grows. The spacecraft's orbit keeps tilting further from the ecliptic with every pass. With each Venus flyby, the inclination grows. Higher inclination helps. It means a better view of the pole, though a longer wait between useful passes. Patience is part of the method here. There is no way to rush an orbital mechanics problem. The team plans to keep raising the tilt for several more years, widening the view a little at a time. Eventually, the view will include both poles more completely, though right now most of the detailed coverage sits over the south. The North Pole remains only partially mapped for now, waiting its turn as the orbit keeps tilting. Each dataset gets folded into growing models of the whole sun. Researchers cross-check PHI's magnetic maps against EUI's brightness data, then line up spice readings to see how heat moves through the layers in between. 3 separate instruments, 1 shared target. The overlap between the 3 instruments is where the useful science happens, since a magnetic reading alone tells you only where the field points. A brightness reading alone tells you where energy is concentrated. Put together, they tell you how the two relate. That relationship is what feeds into storm prediction. It is slow, careful work. No single image resolves the question of how the sun behaves at its poles. But each pass narrows the uncertainty a little further. The proxies that scientists relied on before are not being thrown out. They are being tested against something real for the first time. Where the proxy and the direct measurement agree, confidence grows. Where they disagree, that gap becomes the next question to answer. Engineers on the ground watch the instrument health as closely as the data itself. Solar Orbiter sits closer to the sun than most spacecraft dare to fly. Close enough that heat management becomes its own daily concern. A heat shield protects the instruments from that heat, and small louvers open and close continuously to manage the temperature inside. Every image from PHI, EUI, and SPICE has to survive that environment first. Only then does it become something scientists can study. The team downlinks the data in batches, whenever the antenna geometry allows it. And each batch gets archived, calibrated, and cross-checked before release. That pipeline is unglamorous. It is also why the March images could be trusted the moment they arrived. Over the coming years, the polar maps will fill in. Coverage will spread from a single passing glimpse to a fuller portrait. Forecast models will absorb that new information gradually, one verified pass at a time. Storm warnings may eventually lengthen from a handful of hours to several days. That extra time comes from a change in vantage point, not a change in the sun itself. The sun has always behaved this way at its poles. It simply had not been seen from above before. Now it has. The work of understanding what was seen is only beginning. Years of analysis lie ahead before the polar maps feel complete. The poles of the sun are no longer only imagined. They are being watched. The mission does not end in 2029. Solar Orbiter's plan reaches further than that. Engineers have sketched years beyond, quietly, in mission documents few people read. Each new orbit asks for a little more tilt, a little more height above the plane where the planets travel. The spacecraft answers slowly, one flyby at a time, gaining ground it cannot spend quickly. There is no rush built into this kind of patience. In the later years of the plan, the inclination climbs higher still, higher than anything achieved before it. The two poles begin to feel less like separate destinations, more like two halves of a single growing picture, assembled a little more with every pass. Right now, the north comes into view, and then the south fades. Or the reverse happens and the north slips away. The spacecraft cannot hold both in its sights for long. Later, if the trajectory holds, that gap narrows. Not because the orbit becomes complete. It cannot become complete, not with the fuel on board. It narrows because the tilt grows steep enough to catch more of each pole in a single pass. A wider view, not a full one. Mission planners describe it carefully, without overpromising. They speak of improved coverage. They do not speak of a finished map. That distinction matters more than it sounds. It shapes how every future orbit gets planned. A finished map would mean circling above one pole, always, without end. No instrument in human history has done that at the sun. Every image gathered so far arrives at a slant. Every one still to come will arrive at a slant too, assembled slowly from a moving platform. never observed the way engineers might prefer, from directly above, holding still. There has been talk over the years of something more. Proposals drafted, then set aside, revisited occasionally when a new study cycle opens. A spacecraft placed in a true polar orbit, permanent, circling above one pole indefinitely. The idea keeps surfacing in conference papers and long-range planning documents. It has never advanced past that stage. The reason is not a lack of interest. The reason is the same one that shaped every mission so far. The sun holds onto its planets with tremendous force. Reaching a stable orbit above one of its poles takes an extraordinary amount of energy, far more than reaching almost any other destination in the solar system. A spacecraft cannot simply point itself upward and go. It must first slow down dramatically relative to the sun. Only then can it begin climbing away from the plane. That slowing down is the hard part. It always has been. The method used today relies on Venus. It is the only approach known to work. A spacecraft is sent inward, toward the inner planets again and again. Each pass close to Venus bends its path, steals a little momentum, or lends a little depending on the geometry, nudges the trajectory upward, degree by careful degree. Solar Orbiter has already used Venus this way several times since launch. Each flyby buys only a small rise in tilt. The next several are already planned, spaced years apart. It is slow. It is indirect. It is, as far as anyone can tell, the only practical way to do this. Some ideas exist only on paper. Propulsion systems, still theoretical, still years from any launch pad. Sails large enough to catch sunlight in useful amounts, discussed but never built at that scale. None of these has flown in a form capable of reaching a true polar orbit. For now, the gravity of Venus remains the tool. Patient, repeated, unglamorous. It works because it is reliable, not because it is fast. A mission built this way takes years just to reach its working orbit. Years more to gather useful data once it arrives. There is no shortcut hidden in some future plan. Not yet, at least. Consider the poles themselves for a moment. They sit at the top and bottom of a sphere that never stops turning. A spacecraft orbiting near the plane shares that same fate as everything else circling there. Only a spacecraft willing to leave the plane entirely can see more of either pole. And leaving the plane costs more fuel than almost anything else attempted in space. That cost has not changed. It will not change soon. So the roadmap continues along its current path. Small increases in tilt. Small increases in what each pass can show. A picture built patiently, without the luxury of a hovering vantage point. Someday that might change. A future mission, not yet designed, could attempt something bolder. Could carry propulsion strong enough to climb faster than Venus flybys allow. Could reach an orbit stable enough to remain overhead indefinitely. For now, that mission exists only as an idea. A line in a proposal. A diagram in a slide deck, nothing more. The spacecraft flying today was not built for that. It was built to climb, gradually, and to look, briefly, and to climb again. That is enough to keep learning. It is not enough to finish the picture. The gap between glimpse and completeness will likely remain for years. Maybe decades. Longer than any current plan reaches. Long after the current roadmap runs its course. Long after every planned flyby has come and gone. Someone, somewhere, may eventually close that gap. There is no sign of exactly when. There is no sign of exactly how, beyond the method already in use. For now, the sun keeps its poles half hidden. A spacecraft can approach, can tilt, can watch for a while, then turn away. It cannot yet stay in place above either one. Each pass adds a little more to what is known. A wider slice of one pole, a narrower slice of the other. Traded back and forth, orbit after orbit, year after year. Never quite settling into balance. No mission so far has closed the picture. Perhaps none ever fully will. The Venus flybys keep coming, spaced years apart. Each one small on its own. Together they add up to something no single flyby could manage alone. Still short of a full view, still useful all the same. Engineers plan the next one before the last has even finished. They treat the sequence as a single, unbroken effort, not isolated passes. That habit is the whole method, repeated for as long as the mission lasts. The roadmap does not promise a finished view of either pole, only a steadily improving one. It asks for patience measured in years, not in single flybys. The picture grows a little wider with every orbit that follows this one. Wider, but never whole. Not with the tools now flying. Wider still, perhaps, with tools not yet imagined. The climb continues all the same. Slow, deliberate, unfinished. Just like the picture it is trying to complete.